Okay, I'll go ahead and get started. So, one thing that I want to make sure I go over before we go much farther with the semester is prime numbers. Okay, so you probably heard of prime numbers before. Prime numbers are numbers that cannot be divided by anything else besides themselves and 1. Okay, so some examples of prime numbers: 3, 7, 5, let's see, 13, how about 41? Okay, so all of these are numbers that cannot be divided by anything else except for themselves or 1, because of course anything can be divided by itself, and it also can be divided by 1. It's true for any number. So why are these interesting to us? Basically every other number out there can be made out of these other prime numbers. Oh, I forgot another one, 2. Okay, so for instance, let's say we have 50. So 50, it has some things that can multiply to get 50. So for instance, I could multiply 2 and 25. I could also multiply 5 and 10. Okay, so these numbers that we can multiply together to get 50, whoops, I zoomed that in way too far. These numbers that we can multiply to get 50, we would call the factors of 50. Factors being numbers that we can multiply to get that original number. Okay? Now, if we look in these factors, we have some primes. 2 is a prime number, 5 is a prime number. In fact, 50 can be broken down into what we call its prime factors. Again, if we break it down into, let's say, 5 and 10. So 5 is a prime number. It can't be broken down any farther, but 10 is not prime. It has factors itself. We can break it down farther into 5 and 2. So we would say that the prime factors of 50 are 5, 5, and 2. In other words, we could multiply 5 times 5 times 2, and we could get 50. It's nice to know these things because when we deal with numbers in algebra, in particular, many times it's helpful to know what factors numbers share in common. One of the most probably used areas that it would be in is with fractions. So if I have something like, let's say 6 over 3. Well, 6 over 3 is a perfectly fine fraction. However, I happen to know that 6 and 3 share a common factor. So 6 is 2 times 3, and 3 is a prime number. You could say that it's 3 times 1. but they both share that 3. So what we can do here is we can say, well, since they both share that 3, in other words, whoops, let's try that again. In other words, we can say, since it looks like this, we're multiplying 2 by 3 here, but we're dividing 3 by 3 and 2 by 3. So the opposite of multiplying is dividing, so we can cancel that out. 6 divided by 3, or 6 over 3, is 2. That's what's left over. It's also nice to know for things like roots. Let's say we have a root that we don't really quite know. Something like square root of, let's come up with a good one. Yeah, that's a good one. 2,500. Okay, square root of 2,500. Now I know my roots pretty well, at least up into square root of 144. Square root of 144 is 12. But I don't have at least memorized roots above that very well. Especially something like this, 2,500, that's quite a large number. So what I can do with this instead is I can start breaking it down into its prime factors to try and find matching numbers. Remember that what we're looking for here in a root, in a square root, is something times itself to get this original number. So if I can find factors that match, that means I can find the square root of this thing. I can find the answer. Okay, well, let's see. 2,500 is 25 and 100. 25 times 100. Oh, hey, I know that 25 is a square root. Is a square. That's 5 times 5. There's two prime factors. They match. That means that gets to come out. I get to take a 5 out. 100, let's see. 100 is 10 times 10. Which I could break that down further, but I don't need to because they match. So I know that I can take a 10 out. So what is the square root of 2,500? 50. So factors and prime factors are very useful. Now it's when we get into things that don't exactly divide very well, like primes, that we start to see some interesting things occur. So let me switch the page out. So let's think about 3, that first prime number that I mentioned. Okay. Now, you probably know that when we divide things by 3, like 1 over 3, we don't get what we call an integer out. We don't get a nice, neat little number out. We get a decimal. Decimal here being 0.333333333, so on and so forth. It's infinite. It's not really nice. But there's another way that we can look at this, and that is with some long division. We can say that if we divide 1 by 3, well, 3 will go into 1 0 times, with 1 left over. So we can say that it's 0, remainder 1 for the answer. We'll get into what that means in a little bit. But let's keep going with these. Maybe 2 and 3 will have something different. Okay. So again, this is 2. 3 will go into 2 0 times, minus 0, so the remainder 2. Okay, what about 3 over 3? Well, that works. We'll go 1 time, and remainder 0. Nothing left over. Let's keep going. Let's try 4. 4 over 3. So, again, that'll go in, that'll go in once, and we get remainder 1. How about 5 over 3? Okay. Again, it'll go in once, and remainder 2 again. 6 over 3. I'll go in twice, and it goes exactly, so remainder 0. You might see that there's a pattern going on here. So, if we look at this pattern, we see that we have remainder 1, remainder 2, remainder 0. Remainder 1, remainder 2, remainder 0. And it'll keep repeating on and on and on like that. This is cyclical. There's a pattern, and it keeps going in a circle. It'll keep repeating like that. In fact, let me make a circle for you so it's a little bit easier to see. Okay. And we will plot out this thing. Let's see, there's 3 positions here, 1, 2, and 0 for our remainders. So we need to split this up into thirds. So we'll say 1 is the first position, 2 is the second position, and 0 is the third position. Okay, so let's think, we start at 1, and then dividing by 2, we go to remainder 2. So we've gone here. And then from there we go to 3, so that's remainder 0. And then 4 is a remainder of 1, so it goes back over here. And I want you to notice something. We've gone around the circle 1 entire time. Right? So this tells us how many times we've gone and what position. We can keep going. Next one, we go back to 2. Okay, next one, we go back to 0. Next one, we go back to 1. And it'll keep doing that over and over and over and over again. Okay? So, this number that we get up here, this quotient, what we're looking for our answer, this tells us if we have gone to all of the positions yet, if we've gone around the circle yet. So, no, this is starting at the first position. We haven't seen everything yet. That's why we have a 0. go to the next one. We still have a 0, and that's because we haven't seen all the positions yet. Go to the next one, though. Now we've seen all the positions. We have gone one full stride. And we have remainder 0. We're in that position. Next one, we're starting again. We're starting all over. This is the start point again. So we've gone around the circle once, and we're starting again. So this tells us that we've done the circle once, but we're in the first position now. Again, we've done the circle once. We're in the second position now. We've done the circle now twice. We're in the 0 position. So it keeps going on and on and on like that. This is what is called clock math. You may have heard it called that before. It's also called modular arithmetic. Basically, when we are talking about dividing things up, the results can be filtered into different positions. So like for dividing by 3, we have 3 positions. And these tell us how far away from exactly dividing our answer is. So let's try another one. Different number. Let's try 2. Okay, how about what is 0 over 2? Okay, well that would be like this. How many times do we need to multiply 2 to get to 0? Well, we multiply it by 0. And we have remainder 0. Okay, how about 1 over 2? So if we do 2 into 1, 2 will go into 1 no times. And we have remainder 1. Okay, how about 2 over 2? Well, that is, 2 goes into 2 once with remainder 0. So we can see that 2 is probably going to repeat after this, so it would have 2 positions. Let's just check and make sure, though. 3 over 2. So that'd be 2 into 3. It goes 1 time with remainder 1. So yeah, it's repeating. So there are 2 positions for this one. This is mod 2. Again, let's make our circle. Ooh, that's not a very good circle. It's not going to show up very easily. Just darken that a little bit for us. Okay. So again, there's 2 positions for this one. It's mod 2, modulus 2. The first position is 0, the second position is 1. So we go here. We're just starting out. And then from here to here, okay, we're now in the second position. Okay, so from here to here, we've gone 1 full turn around the circle. We're back at the start. From here to here, we go this way again. We've already done 1 rotation already, but we're back at the second position. So why is this useful? Why do we want this? There's one place that I have encountered this in my own life. and that is when I was programming a time, what do you call it? Like a punch card, punch clock. Okay, so what I was doing is I was the manager of the tutoring center, and I needed to know when my tutors were logging in and logging out so that I could pay them accordingly. You know, they put in the time that they come in, and they put in the time that they leave, and then they get paid based on the time that they were there. Okay, so to do this easily, what I had them do is I had them sign in on a clipboard, and then I made a program with the TI calculator that I had that would take the start time and the end time and then calculate how much time had been in between. And so, you need to test programs, and so I started putting in numbers, and it was working great, worked fabulously, except for one particular instance. So it was calculating, I'll draw another circle here real quick for a clock. Okay, so 12 o'clock here, right? So it was able to calculate most things. So like if they came in at 1 o'clock and they left at 6 o'clock, it would calculate it by saying, okay, how much time is there between 1 o'clock and 6 o'clock? It's 5 hours. Okay, so because the difference between 1 and 6 is 5. So in other words, 6 minus 1 is 5. However, it wasn't able to do things past 12. So if they came in like, let's say 11 o'clock and then left, 11 o'clock a.m. and then left at 1 p.m., instead of calculating the time between these 2 points, it would calculate the time outside of those 2 points. So what the heck was going on there? I was very confused. Why was it giving me obviously wrong answers? Why was it calculating outside of instead of inside of the 2 points? And it's because the program that I had written didn't realize that it can go around the clock more than once. Just like we're talking about with our mod. So like, let's get back to mod 3. There's 3 positions on here, right? But using this quotient, we can know how many times we've been around the circle. So going from here to here to here and then back is one complete rotation. And we can see that in the quotient. The remainder tells us what position we are on, and then the quotient tells us how many times we've gone around. Well, this program wasn't able to do that just by the way that I was writing it. It only knew that there was a circle there, but it didn't know that it could go around more than once. Okay? So what I did is I found a friend of mine, a fellow professor, who was in the computer science department, and I said, I'm having this problem, what do I do? And he said, modulus math, which I'd heard of before, but I hadn't really done a whole lot with it before. I knew the concept. I kind of thought about it and said, yeah, that makes a lot of sense, because it needs to know that we've gone around the clock. The program didn't know the difference between AM and PM, in other words. It just knew, okay, there's a position here and a position here. It needed to be able to realize that, oh, there's a difference between the morning and the afternoon. There's a way that we can go around this clock more than once. And so I reprogrammed it using some mod math, and it worked just fine after that. So modular arithmetic does pop up in places. It pops up in some pretty interesting places. But for you right now, really, just think about it in terms of these quotients and remainders. Okay? So again, the quotient is telling you how many times we've gone around. So, excuse me. Like in mod 3, this tells us that we've gotten an entire 3 once. Or I should start here, really. We've got an entire 3 once. Then another rotation is another 3. So that'd be 6. Another rotation would be another 3. That's 9. Another rotation would be another 3. That'd be 12, so on and so forth. Okay? So this quotient tells you how many 3s we've gotten, how many times we've gone around the circle. So this is a single 3 that we've gotten, this is 2 3s that we've gotten. Then the remainder tells you what position we're on in this circle. So for instance, like if I did 7 over 3, just keep on going with this pattern. I know that this will be 2. We've done 2 rotations, we have 2 3s. And then the remainder, the remainder 1 tells us that I have a 3rd left over. Okay? So again, modular arithmetic is very interesting, and it can be quite useful. It pops up in places that you wouldn't really expect it to all the time. However, it's not something that I think that a lot of people are going to notice in their everyday life. A lot of what we do with mod math almost seems intuitive, but like for me especially in computer science, it is really useful because computers, they don't have any kind of intuition. You have to tell them exactly how to do things because they can't figure it out on themselves. And that's why we have things like this. Okay, so short lecture today. I think that'll do it. Now Monday is the 25th, and that is the first day that Sul-Ross is going back to face-to-face classes. Okay, so be sure to be here Monday. Of course, that's, what is that, 2:11? Check your schedule. I think that's the classroom. Okay. But we'll meet in the classroom on Monday. Other than that, though, I think that's it. So I hope you have a good weekend, and I will see you Monday.